Just some housekeeping up front. I posted, for those of you that have taken the test, I posted your grades, and then I went back and looked at the key a little closer, and I found one that everybody got credit for. So then I redid your grade. So that's kind of where we are. I'd love to give you your test back today, but what? I still have some people to take it, see? And when I have that scenario, I can't put the test out there. You understand that? But you have your grades. You've got your feedback. So that's a little housekeeping for today.
So can we make those up after class today?
Yes, we're going to do that. If you missed the test last week, I'd like you to stay and make it up when we're done here.
Okay.
Okay? All right, so we're going to finish our discussion today on electromagnetism. Then we'll review for the exam. That is when?
Next class.
When?
Next class.
Yes. All right, so where do we leave off? Somebody tell me. I know, I don't need you, but I want to make sure we're...
Electromagnetic induction.
Yep.
Talking about magnetic flux laws.
Yep, magnetic lines of flux, remember? Remember that? And we've talked about that. That's what you feel when you play with magnets. Sometimes they attract, sometimes they oppose. All right. Do you have in your notes that a magnetic field is always around a conductor in which current is flowing? That's pretty key. And I think we went over the helix, based on the helix, the solenoid. Okay, good. All right, so let's get back to all right, what are these I'm drawing in now? Yes. So there they are, right? If I straighten that out, it would be what? An iron bar. But we bent it and we made it into a horseshoe magnet. So we're going to lead off today with something called electromagnetic induction. Whenever a conductor, and we're going to call it a wire, cuts across magnetic flux, or is cut by magnetic flux, a voltage is induced into the conductor. We good? So, remember, just a minute ago we said this is what? Yeah, magnetic lines of flux. All right, so this is my wire or conductor, right? And we move it. Are we cutting the magnetic lines of flux? Huh? We are. What happens to the conductor? We get a
Current.
we get a current or a voltage going up. All right? So, tell me what piece of farm equipment that we talked about.
Windmill.
Thank you, because I didn't want to draw it again, put you guys through that. Think of the windmill, right? The wind blows and it moves the what? It moves the wire, and it does what? Cuts the magnetic lines of flux, and we get a what? Current. All right, so that's a little bit on the mechanics of how a generator works, right? Generating power. Now, go back to your definition that I just gave you. How else can we generate current in that wire? Look at the definition. Part B. Come on.
By moving the magnet?
By moving the flux, right? So in other words, what could we do? Put the wire here and do what? Move the magnet. So in other words, this, right? Move the magnet. Induction. Good. So you can move the wire or you can move the magnet, however you want it to be. Now, the greater this, the greater will be the induced current. Also, the angle. So we have move the wire or move the magnet. Now the third thing is the angle. Get your notes down and then I'll show you. The angle with which the conductor cuts the lines of flux. Matters. And this is the key. When that wire is cutting at 90 degrees, you're getting the greatest induction. And I'll show you what that 90 degrees looks like here. Is that 90 degrees? It is. Compared to when we cut it like that. That's not, is it? 90 degrees gives you the greatest. What's this called again? The sine wave, right? Let me label it here. I'll call it a delta. How's that? Delta 1, delta 2. Is that okay? You guys? All right, so now I'm gonna take a wire, and we're gonna bend it so that I have two wires. You with me? I've got two wires, I'll put them up here. Watch. See the two dots? These are the wires. With me? And it's one wire, but with two loops, with one loop. And this is attached to the blades of the windmill. You with me? And then the wind, and where on that are we here? When they're here? What letter?
A.
Hey, nothing's happening. Ready? This is going to be an exercise for me. I'm going to be going back and forth. All right, so we're at A here, right? The wind blows and it starts to turn the wire. All right? Now, it starts to cut. Right? It starts to cut. And then you start to see the voltage. Right? The voltage. And when you get to the peak, those wires are what? They're 90 degrees. Watch. They're 90 degrees. And when they go 180, where are we now on our thing? What letter? C. Nothing's happening, right? And then we continue. And then we're down here. In other words, we reverse direction in the wire, that's all. We make one revolution, keep going, and we're back to where now? E. One cycle. Did you get that? One cycle. We cut, and when you're cutting 90 degrees, you're here. Everybody okay with that? Steve? We're okay. Now, let's say, for instance, let's look at the farm scenario. So we know we get the greatest voltage when they're cutting at 90 degrees. Then why in the farmhouse don't the lights flicker, right? And be brightest here and here. Why?
Going too fast.
Pardon me?
It's going too fast.
It's going too fast. Because how many cycles do we do a second? Do you remember that?
60.
All right, which is how many?
120.
There you go. Good. That's why they don't flicker. It's going so fast. So, maximum voltage or current at here, and here again, it's not so much, because we're not cutting at 90 here, at the delta 1 and 2. All right, good job. All righty. That's a generator. We generated electricity because we had what? Mechanical motion, moving a conductor through magnetic lines of flux, generating current in the conductor. All right, now we're going to move on to we're gonna move on and talk about something called a transformer. Have we talked about that at all? I think I mentioned something
mentioned it.
about it. When? Transformer.
We're talking about power line.
Power lines. Where did I talk about the transformer? You'll find it where?
On the ground,
What?
or outside your,
Interrupt.
Between you and your neighbor, right?
yeah.
You're talking about the step down of the power from the higher.
Yeah, from the power plant, all right? So let's take a look kind of how what goes on in there. So we're gonna take a look at a transformer. Let me draw it. Two iron bars. Now we're gonna wrap those bars in what? A wire.
Why?
Coil it around. Two iron bars, more coils than the, okay? Primary, secondary. All right, so if this is the box in your yard, and this is the one coming from the power plant, it has what type of voltage?
Right.
High voltage, right? And what do we want to do? We want to step that voltage down so that it can come in your house and be functional. So do you see the coil, which we'll call this primary and secondary? Which electromagnet has more coils in it, the primary or the secondary?
Primary.
And the secondary has fewer coils, and this is called a what type of transformer? Second, step down. It's a step down. And here's the key here. Of course, I think we'll all agree that the primary, this needs alternating current to work. Alternating current. So on the primary side, it's supplied by alternating current and has a lot of coils or turns in it. And this is a step down transformer. And the scenario you're looking at there is something called mutual induction. You must have alternating current for mutual induction. All right, so I guess I should. And that secondary there, it just sits there. It just sits there. So nothing's happening. We're right here. Everybody with me? We're right here. Now, so we start to move current through this. And the fact that it's an electromagnet, in other words, it's a coil with a bar in the middle, intensifies it. So what happens? We're running current through the primary side. And the magnetic lines of flux do what? Come up and go down. They come up and go down, like here. They come up and they go down. They come up and they go down. And those magnetic lines of flux here do what to these? They what?
Promote current?
How?
No.
Mutual induction, right? But what's happening? We have magnetic lines of flux coming up and going down. Coming up and going down. Are those magnetic lines of flux cutting this? Huh? Are they? They are. Inducing a what? Current. In the nature of a step-down transformer. It has fewer coils. That's a step down. Now, if I had more coils in the secondary, it would be called a what?
Step up.
Step up. Yeah. All right, so where do you think I'm going?
Inverse.
It's good. Formula, right? There's going to be a formula for this. So let's fill it in. So in other words, the nature of this formula will be to solve for what's missing. All right, so let me give you the formula and we'll talk about it. This is called the transformer law. Anybody want to weigh in on what the V stands for?
Volt.
Voltage. And the S and the P?
Secondary current.
Very good. N? Number of turns. Okay. Number of turns in the secondary, number of turns in the primary. And does everybody agree they're different there? So this is a problem to determine what's missing in the scenario. So let me give you a problem. Use that equation. Okay. All right, so you tell me where to put these numbers. The primary coil has 100 volts. Where do I put that? Voltage primary, right? And it has 100 turns. So where does that go? Number P? And it's 100. The secondary coil has 500 turns. What's the first thing that comes to mind? 500 turns on the secondary side. It's a what? It's a step up. It doesn't look like it there, but let me make one. I'm going to get writer's cramp doing this, right? Huh? 500 turns. Now is a what? Step up. Where do I put the 500?
NS.
Right here? What's the voltage in the secondary? Go ahead, do it. So just looking at that, is it gonna be more than 100 volts? Huh? It's gonna be more than 100 because the nature of the problem is it's step up. So what'd you guys get?
500.
500, anybody? All right, so you see, we went from what? 100 volts to 500 volts because we had what? More turns in the secondary. It was a step up. Okay? Keep in mind, you gotta have this alternating current to do what? Bring it up, bring it down. To cut. See? To bring it up, bring it down. So that's a step up transformer. The first scenario I had up there was a step down.
So for a step up, will the alternating be on the secondary?
Oh yeah, it creates alternating current. Yeah, as it goes on. Because of this, watch. You get this, nothing, right? And then you get this, and then you get this. So yeah, you generate alternating to alternating. And another way I like to talk about alternating current, just to give you a picture in your head, how people go to the beach and they get sunburned. And then you've probably seen this. You go to the beach, you're all sunburned, and you come up like this, and somebody says, what? You're hot. It's like you're what? You're radiating. Okay? What is that? That's mutual induction. Didn't I give him heat?
No.
But was it alternating or direct? Did it stop and start? No, that was direct. Okay? But that's the point I'm trying to say here. These flux lines cut and start a voltage. So, another picture for your mind on how this all works. Good. Okay, moving along. All right, so what have we talked about here today? We talked about a generator, generating current in a wire. We gave the example of what a generator is. It's like a windmill. And then we talked about a transformer. What's the key for all of this transformer business up there? You have to start with what?
An alternating current.
Alternating current. You got to somehow get those wires cut. So we talked about transformers, which have what? Electromagnets in it. There's a primary side, a secondary side. we're going to induce current in the secondary side by using something called
Induction.
mutual induction. Okay. All right, so what's kind of left here? Another little device. So let me, before I move on to this next piece, a bicycle. All right, you guys ever rode your bike at night? And on your bike, you should have a light. And what's the bike equipped with? With
Reflectors.
reflectors, yeah. But you want to see where you're going, so you have a headlight on your bike. And how do you get that light to come on?
Switch.
If you have a battery, but you don't have a battery. You have that little device that sits next to your tire. Are you with me? No? You're not familiar with it? All right, so you had a little device. Oh gosh. All right. This is the best picture I can give you. You go to a liquor store, and you know, bottles come in different sizes, and you have the clerk. What's usually behind the clerk? Come on, the little, you know, the little bottles, right? Right? That's what you get if you fly on an airplane and get a cocktail. You get a bottle about that size. So you have a little device up near your, it's about that big. The point I'm making here is, it's the size of the little bottle. It's a generator that sits on the back of your bike. Have you not seen this? Maybe these are old school bikes.
I might have one. I can't remember.
All right,
I haven't
but
ridden
it
in a while.
was a little generator about the size of one of those mini bottles. And it would sit there, and if you wanted your light to come on, you pushed a button, and then the roller on that little generator would lean up against your tire. You with me? Then you would ride your bike, and the roller would start to move as your bike tire moved, and it generated what? Huh? Current to make the light on your bike come on. And if you stopped, guess what happened to the light? It went off.
I've never seen this before.
No.
I've seen the battery ones, I've never seen that.
So are they, maybe the takeaway is bikes today have a battery on them? Yeah. Yeah, it's a little generator. It looks like a little bottle. And it has a device that moves. And it generates current so that you can see where you're going. Or you can deactivate it, like take it off the tire. Or when you stop, like at a stop sign, the light will go down. Okay? That's a generator. So, with that on the table, what's the last little component here that we need to talk about?
Grounding?
Pardon me?
Grounding?
No. No, I'm standing here for a reason. What? Yeah. Yeah. What's in this clock?
Batteries?
Okay. Yeah, probably. I'm sure it is, because I can probably take it. Batteries, right? Do you see anything moving?
Yes.
Huh?
Yes.
A second hand? So what's in there? It's a motor. That's the point. That's what we're going to talk about. Now, what's a motor? That clock has a what in it? A motor. That does what? Turn the second hand. So, let me give you the definition of a motor, and it might make more sense to you. All right, a motor is a device that converts electrical energy to mechanical energy. That makes sense? Does that help? So it's an electrical device. What's the source in that clock? A battery, right? So we're going to put a wire in a magnetic field in there, in the motor. The motor has a magnetic field and a wire, but what's going on in the wire? It has current, right? From the battery. So you put that in a magnetic field, there's a side thrust to the wire. In other words, it wants to get thrown around. It wants to push it out of the field. So, that's where the motion comes from. The wire, it's getting moved around. But how do we control it? How do we control this movement of the wire in the magnetic field? Through a system of what? Gears. We can harness it and get into a what? Motion. And you see the motion on that second hand, okay? Through a system of gears. So that's your definition of converts electrical energy to mechanical energy. If we took the batteries out of that clock, this stuff would what? Stop. Okay? So that's what a definition of a motor is. All right. Any questions? You ready to review? Okay. What type of induction do transformers work on?
Mutual.
Mutual. Isn't that the only one I gave you? Yeah. Good. Did I talk about anything called a lodestone?
Yes.
Take a look at that. Did I talk about anything called, Steve, you remember this, El Nico? You know,
The aluminum, nickel, and cobalt.
yeah, you know, I just realized that you could use that as a name. What's your name? Al Nico.
It was
Okay, so we talked about some things that come into play with magnetism. Remember the laws of magnetism, like poles attract, unlike. What happens if you break a magnet? Get your hands around the concept of magnetic retentivity and permeability. Did I talk about that? be able to differentiate solenoid from helix. Be able to differentiate a generator from a motor. See that formula up there? Okay. You'll need that for a problem. And you'll need to know how to express that in words. In other words, I'm not going to ask you to write it, but you're going to see it written in 4 different ways, be able to recognize the proper narrative of what that is. How many times does AC change direction per cycle? A second?
60?
How many times
Oh,
does
cycle,
it
120.
change direction?
120.
120, very good. American generators operate at 220 volts. And I think if I described 2 types of transformers, you could pick out if it was primary or secondary, right? Or I mean step up or step down. The first thing I drew up there today was what type of transformer?
Step down.
And then I drew a what?
Step up.
Step up, good. So let me ask you how you'd answer this question, true or false? You ready? A magnetic field is sometimes around a conductor in which a current is flowing. Why is it false? It's always around a conductor when current is flowing, right? What if the current's not flowing? No, it's just a what? A wire. And get your hands around the concept too of remember we talked about ferromagnetic, non-ferromagnetic, and things like that, be able to differentiate what that is. Okay, and you guys should be ready for this exam. So next week we will have class on, we will have the exam, and then we're going to have class in our next session. Any questions? How's everybody doing with their project? There should be plenty of material.